Solenoid of finite length, solenoid of finite length and magnetic flux density at the midpoint on the axis of this solenoid of finite length. Solenoid of finite length and magnetic flux density and magnetic flux density. That is, we have to know the expression of magnetic flux density due to a solenoid of finite length. Solenoid with finite length. Here we have to consider a solenoid of finite length, and we are drawing a diagram of solenoid in which this is a cylindrical core on which an insulated copper wire will be wound in the shape of helix. This is the cylindrical core of magnetic permeability mu. Magnetic permeability mu. And we can denote this as the axis. This is the axis, imaginary axis of the cylindrical core. Imaginary axis of the cylindrical core. Now we can denote the midpoint of the solenoid. Here P is the midpoint on the axis of the solenoid, and x1 and x2 are the two ends of the solenoid. And this is the cylindrical core having magnetic permeability mu. This is the cylindrical core of the solenoid having permeability mu. Mu is the permeability of the cylindrical core. Mu 0 is the permeability of the surrounding medium or vacuum. An insulated copper wire is wound on this cylindrical core in the form of helix. The insulated copper wire is wound in the form of helix, and an electric current I is sent through this insulated copper wire. That is, a current I is flowing through the insulated copper wire which is wound in the shape of helix on the cylindrical core. The wire which is wound in the shape of helix is insulated copper wire. It should be insulated so that there will be no leakage of current. Mu is the magnetic permeability of the cylindrical core. And we can denote the current flowing through each turn, and in this case current is flowing downwards. If it is observed from the front face of the cylinder, I is the current which is flowing through each face of the solenoid. And in this case this is the solenoid. This is the solenoid with a finite length. The solenoid is of finite length in this case. L is the length of the solenoid. Capital L is the length of the solenoid. We can denote the diameter of the solenoid. Here D is the diameter of cross-sectional area of the solenoid. D is the diameter of the cross-sectional area of the solenoid. Here we are considering a solenoid of finite length, and if the solenoid has finite length, that means as the solenoid is of finite length, that's why the finite length is capital L. As the solenoid is of finite length, we can say that diameter D is much less than diameter D is just less than L. That is, diameter D is comparable to the length L. Here, what we can say, that is D is less than L. It is not much less than L, where D is the diameter of the circular cross section of the solenoid. D is the diameter of the circular cross section of the solenoid, and L is the length of the solenoid. And in this case, as the solenoid is of finite length, that's why diameter D is just less than L. That is, diameter D is comparable to length of the solenoid. That is, D comparable to L. is comparable to L. Here now we can denote the radius of the circular cross section of the solenoid. We are denoting the radius of the circular cross section of the solenoid. Here this point is y1 at the end x1, and we can denote another point y2 at the right end of the solenoid. Y2 is a point at the end x2. P is the midpoint on the axis of the solenoid. The magnetic flux density, that is the magnetic field induction. The magnetic field induction, that is the magnetic flux density at the midpoint P, at the midpoint P on the axis of the solenoid, at the midpoint P on the axis of the solenoid is given by, on the axis of the solenoid of finite length, on the axis of the solenoid of finite length L is given by capital L. It should be capital L, not small l, equal B equal half mu in I under bracket cos theta 2 minus cos theta 1, cos theta 2 minus cos theta 1. B equal half mu in I cos theta 2 minus cos theta 1, where mu is the magnetic permeability of the cylindrical core. N is the number of turns per unit length of the solenoid. Small n is the number of turns per unit length of the solenoid under bracket capital N, small n is equal to capital N by L. So here we can denote the number of turns 1, 2, 3 up to capital N. Capital N is the total number of turns and small n equal capital N divided by capital L, which is the number of turns per unit length of the solenoid. Number of turns per unit length of the solenoid, where number of turns per unit length, number of turns per unit length of the solenoid under bracket small n equal n by L. Small n equal n by L. Capital N is the total number of turns of the solenoid. Total number of turns of the solenoid. Mu is the magnetic permeability of the cylindrical core. Mu is the magnetic permeability of the cylindrical core, and B has the expression half mu in I cos theta 2 minus cos theta 1. Mu is the magnetic permeability of the cylindrical core, and mu 0 is the magnetic permeability of the surrounding medium or that of vacuum. Now we can denote what is theta 1 and theta 2. What is theta 1 and theta 2? Theta 1 is the angle subtended by the oblique distance y1p of the point P with the axis of the solenoid. Theta 1 is the angle subtended by the oblique distance y1p, the oblique distance y1p of the midpoint P on the axis of the solenoid with the axis of the solenoid. Theta 1 is the angle subtended by the oblique distance y1p of the ends y1 of the solenoid, from the point P, from the midpoint P with the axis of the solenoid, Similarly, theta 2 is the angle subtended by the another oblique distance y2p or py2 of the end y2 of the solenoid, from the midpoint P, from the midpoint P with the axis of the solenoid, with the axis of the solenoid. From triangle y1x1p, from the triangle y1x1p, y1x1p cos 180 degree minus theta 1 is equal to base by hypotenuse, that is x1p divided by y1p, x1p divided by y1p. Now theta 1 is the angle subtended by the oblique distance py1 of the end y1 from the midpoint P with the axis. So here we have denoted the angle theta 1, that is the angle subtended by the oblique distance y1p with the axis x1 x2. Now we can denote the angle, which angle is 180 degree minus theta. Now the angle y1px1 is 180 degree minus theta, that is the angle subtended by the oblique distance py1 with the axis px1, that is 180 degree minus theta, or comma minus cos theta 1 is equal to, in place of x1p, what we can write, it should be L by 2 divided by root over r square plus L by 2 whole square, divided by root over r square plus L by 2 whole square, where r is the radius of the circular cross section of the solenoid. And we can draw the triangle again, that is the triangle y1x1p. y1x1p is a right angle triangle, and this angle is 180 degree minus theta 1. In this triangle, r is the perpendicular, x1p is the base, which is equal to L by 2. And here we can write cos 180 degree minus theta 1 is as equal base by hypotenuse, that is x1p divided by y1p. x1p divided by y1p, and y1p is the hypotenuse, x1p is the base. Finally, we get minus cos theta 1 as equal L by 2 divided by root over r square plus L by 2 whole square, or comma here cos theta 1 will be equal, minus L divided by root over L square plus 4r square, where where the radius theta 1 as minus L divided by root over L square plus 4r square. Similarly, from the right angle triangle y2x2p, from the right angle triangle y2x2p, cos theta 2 is equal to px2 divided by y2p. Cos theta 2 is equal to x2p divided by y2p is equal L by 2 divided by root over r square plus L by 2 whole square. Finally, we get the value of cos theta 2, and cos theta 1 is equal to minus L divided by root over L square plus 4r square. And what should be the expression of magnetic flux density B at the midpoint P on the axis of the solenoid? That is, we have to find. So B is equal to half mu Ni L divided by root over L square plus 4r square minus under bracket L under bracket minus L divided by L square plus 4R square bracket closed is equal to half mu ni L divided by L square plus 4R square plus L divided by root over L square plus 4R square bracket closed is equal to half mu ni, not mu 0 ni, because the solenoid has cylindrical core. So mu ni under bracket 12 divided by root over L square plus 4R square. Therefore, B is equal to mu NIL divided by root over L square plus 4R square. B is equal to mu NIL divided by root over L square plus 4R square. Here R is the radius of the circular cross section of the solenoid. So finally we get B as equal mu NIL divided by root over L square plus 4R square, which is the magnetic field induction, that is magnetic flux density at the midpoint P. Magnetic field induction or flux density at the midpoint P on the axis of a solenoid having finite length. Magnetic field induction at the point P of the axis of the solenoid of finite length, capital L. The solenoid has finite length, and the expression of magnetic field induction at the midpoint P on the axis is B equal mu NIL divided by root over L square plus 4R square. So this is the magnetic field induction at the midpoint P of the axis of the solenoid of finite length. The solenoid has finite length, and the magnetic field induction at the midpoint P is B, which is equal to mu 0 NIL divided by root over L square plus 4R square. L is the length of the solenoid. Number of turns of the solenoid per unit length is small n, which is equal capital N by L. Capital N is the total number of turns of the solenoid, and R is the radius of the circular cross section of the solenoid. Here we have denoted the length, number of turns per unit length, and radius of the solenoid. So B is equal mu NIL divided by root over L square plus 4R square, which is the magnetic flux density at the midpoint P of the axis of the solenoid of finite length L and radius R, with a cylindrical core of magnetic permeability mu. The cylinder has cylindrical core having magnetic permeability mu. Mu is the magnetic permeability of cylindrical core, and mu 0 is the magnetic permeability of vacuum or surrounding medium. If the solenoid is of infinite length, or the solenoid is of long length. If the solenoid is long, in that case length of the solenoid L tends to infinity and L much greater than radius. Hence, what we can write, mu NIL divided by root over L square plus 0 under bracket L much greater than R. That means length of the solenoid is much greater than the radius R of the solenoid. Here Obviously, L much greater than R, and R can be assumed as 0 in this expression. Therefore, B will be equal to mu NIL divided by root over L square. Therefore, B is equal to mu Ni. B will be equal to mu Ni, that is the magnetic field induction at a point on the axis of a very long solenoid. That means B is equal to mu Ni. That is the expression of magnetic flux density at a point on the axis of a very long solenoid. Therefore, B is equal mu Ni, which is the magnetic flux density or magnetic field induction. B is equal mu Ni, that is the magnetic field induction, that is magnetic flux density at the point P on the axis of a long solenoid, on the axis of a long solenoid with a cylindrical core of magnetic permeability, with a cylindrical core of magnetic permeability mu. Now we can compare with long solenoid with vacuum, long solenoid with vacuum as its core, and also long solenoid with a cylindrical core of magnetic permeability mu. Left hand side we have long solenoid with vacuum having magnetic permeability mu 0 as its core, and right hand side we have long solenoid with a cylindrical core of magnetic permeability mu, and that is we have to compare. Now we can draw a long solenoid in which an insulated copper wire is wound in the shape of helix, such that the solenoid there is vacuum as core inside the solenoid, and an electric current I is sent through the solenoid. An electric current I is sent through the solenoid, and current is flowing through each turn in this way. Current is flowing through the turns of the solenoid in this way, and we consider a point P. At the point P, magnetic field induction B is acting towards right, and vacuum is the surrounding medium having permeability mu 0. L is the length of the solenoid. We can denote the number of turns 1, 2, 3 dot 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 capital N. Capital N is the total number of turns of the solenoid. And again vacuum. The intermediate medium inside the solenoid is vacuum as its core, having magnetic permeability mu 0. On the right hand side we can draw a cylindrical core having permeability mu. This is the cylindrical core having permeability mu. On this cylindrical core, and we can denote the axis of this cylindrical core, and an insulated copper wire is wound on this cylindrical core in a shape of helix. An electric current I is sent through this solenoid with a cylindrical core. In this way we can send the current through the solenoid, and at the point P on the axis of the solenoid, magnetic flux density B will be acting towards right. We can denote the number of turns in this way. So, and mu is the permeability of the cylindrical core, and vacuum, there is vacuum as surrounding medium having permeability mu 0. L is the length of the solenoid with the cylindrical core of permeability mu. Number 1, obviously magnetic field induction at a point P on the axis of the solenoid with vacuum as its core as B equal mu 0 NIL divided by root over L square plus 4R square. On the right hand side, B is equal to mu NIL divided by root over L square plus 4R square. R is the radius of the circular cross section of the cylinder, and D is the diameter. And in this case both have the finite length according to the diagram or expression, The solenoid has finite length, and we get the expression of magnetic field induction at a point on the axis of the solenoid. Left hand side we have the expression of magnetic field induction at a point inside the solenoid with vacuum as its core, and right hand side B is equal to mu NIL divided by root over L square plus 4R square, and this is the expression of magnetic field induction at a point on the axis of a solenoid with a cylindrical core of magnetic permeability mu. For a solenoid with vacuum as its core, we have used mu zero. We have used mu zero in the expression of magnetic flux density B. But if we consider a solenoid with a cylindrical core having magnetic permeability mu, we have used mu. We have used mu in the expression of magnetic field induction B. That means there should be mu zero for the solenoid with vacuum, but we have to consider mu as magnetic permeability for a solenoid with a cylindrical core. So for a solenoid with vacuum, we have the expression of B, which is equal to mu 0 NIL divided by root over L square plus 4R square. But for a solenoid with a cylindrical core having magnetic permeability mu, B has the expression mu NIL. B is equal to mu NIL divided by root over L square plus 4R square. Mu NIL divided by root over L square plus 4R square. That is the comparison between the long solenoid with vacuum as its core and a long solenoid with a cylindrical core having magnetic permeability. And that was for a solenoid having finite length. But if the solenoid has infinite length, or the solenoid is very long, or the solenoid is long, in that case what should be the assumption? Due to a long solenoid, obviously B will have the expression B equal to mu 0 Ni, but due to long solenoid on the right hand side B will be only mu Ni. For a long solenoid with vacuum as its core, B is equal to mu 0 Ni. Mu 0 is the permeability of vacuum. On the right hand side, for a long solenoid with a cylindrical core, magnetic field induction or magnetic flux density will have the expression as B equal mu Ni. B equal mu Ni. This is the magnetic field induction of a solenoid with a cylindrical core.